Good afternoon, everybody, and thanks for having us all here, and Jairo and all the organizers, Rafael, Libor, for putting this workshop together. So I'm going to talk about a few things, about a few ideas towards altermagnetic spintronics, and I divided the talk into two parts. The first part is more general remarks on altermagnetism in connection to spintronics. And in the second part, I will talk about two experiments, again, more towards spintronics with altermagnets, and rather than spintronics itself, we will see. And this second part will be mostly based on two unpublished papers by all these people. Actually, the main purpose of showing this first slide is obviously to give credit to all our colleagues that have contributed to this. All the organizers of these workshops are on the list, and and many more in the audience here. So so as a warm-up exercise, let me just briefly introduce spintronics based on the conventional ferromagnets, partly from the perspective of spintronics itself, and partly from the perspective of the ordered phases in condensed matter. So ferromagnetism is, as well as altermagnetism, are examples of the ordered phases that spontaneously break the symmetries of the underlying interactions or of the underlying Hamiltonian. So in case of ferromagnetism, the term in the Hamiltonian that is responsible for the ferromagnetic ordering is the electron-electron interaction. And when you look at the expression, there is no explicit dependence on spin. So the electron-electron interaction term in the Hamiltonian is fully spin rotation invariant. And so is the normal phase of the system, where it's not in the ferromagnetic phase but still in the normal phase. When we look into the Dirac space, or when we look into the momentum space, we see that there is no spin dependence, so there is still the full spin rotation symmetry preserved, the symmetry of the parent Hamiltonian. That changes when we go into the ferromagnetically ordered phase, because in the ferromagnetically ordered phase, what you see is that in the Dirac space we develop a net magnetization, and now we can have a state in which magnetization is pointing up, or we can have a state in which magnetization is pointing down. So we break the spin rotation symmetry, and those two states are not equivalent, and they can, in spintronics, represent the two logic states of the binary bit, for example. Now, when you look into the momentum space, here you also see that the spin rotation symmetry is broken, because in this state we have the spin up being the majority band here, while in this other state is the spin down, which is the majority band here. So the system is not anymore invariant under the continuous spin rotation. Now, all what's happening here, you see, is actually the spontaneous symmetry breaking associated with ferromagnetism is happening in the spin space. So now the question is, how in the world can we detect this electronically? How can we distinguish those two states, which are different in terms of their spin rotation? How can we distinguish this by doing an electrical experiment? Because electrical experiment is in the orbital space. But when you look at the two Fermi surfaces in the orbital space, they look exactly the same. So here came the extremely clever concept of spin valves, or giant or tunneling magnetoresistance devices, where you still have these two magnetic states, one pointing up, one pointing down, representing 0 and 1. But in the device, you have an additional ferromagnetic electrode, which is a reference electrode, where the spins are always pointing in the same direction. And now you can test in which of these two mutually spin-rotated states you are by sending an electrical current. And you can test it because the electrical current is carrying the spin information, because in ferromagnets the electrical current is spin polarized. So we have an electronic device here which is directly testing the broken spin rotation symmetry, or directly testing the broken symmetry in the spin space. So I mean, we're kind of used to this device. It's part of semiconductor industry, but for us physicists, I think it's still nice to realize that this is a wonderful design in which you're testing something which is happening in the spin space by an electronic phenomenon, by a phenomenon which normally you would think is just doing something in the orbital space. Now, it's been so successful, this idea, this concept, that today it's actually a part of the semiconductor industry. We're not talking anymore that is complementing or trying to compete, is an inherent part of semiconductor industry. Today, on the most advanced node, integrated circuits, and we're talking about microcontrollers and microprocessors, all of them beyond the 20 nanometer nodes have these bits in their non-volatile memories on chip, embedded on chip. So this concept of spintronic memory based on ferromagnets has now today become a major part of the semiconductor industry in a mass production mode. Now, people in the industry, however, also realize that there are some constraints imposed by the fact that magnets have magnetization in terms of spatial scalability, because magnetization generates stray fields and they have to fight with the stray fields when they design these devices. And also magnetization limits the speed, because it becomes energetically extremely costly to run these devices beyond the gigahertz speed. So the question is whether we can have something like this, whether we can have a spontaneously symmetry broken phase, an ordered phase, by which we can represent zeros and one, but there will be zero net magnetization. So automatically we will remove these limitations that are imposed in ferromagnets by magnetization. And in parallel to spintronics, there's been another field which I believe, and I can ask Eduardo whether this is the case or not, developed completely independently. The field of what we can call, for example, electronic nematics. Is again a spontaneously symmetry break-in phase, an ordered phase, but it's very different from the ferromagnetic phase. Again, the phase, the ordered phase, is again due to the electron-electron interaction term in the Hamiltonian, but now I will emphasize, besides the spin independence, that means that there's a full continuous spin rotation symmetry of this term, what you see here is that it's also isotropic. So the term is also has the full real space rotation symmetry. So we have spin space rotation symmetry and real space rotation symmetry, and now what's happening in this nematic phase is that, of course, when the system is in the normal phase, it has all the symmetries. It has the spin space rotation symmetry and full real space rotation symmetry, so the Fermi surface is isotropic. But in the ordered phase, in the nematic ordered phase, what happens is that there is this spontaneous anisotropic deformation of the Fermi surface. Now this is happening spontaneously because the Hamiltonian does not have this anisotropy in it, in the interaction. Now, as you see, now this spontaneous symmetry breaking is now happening in the real space. So you can think I can directly build a device in which I will control whether my deformation axis will be vertical or whether it will be horizontal, for example. And so I have these two, So I have these two distinct states, and I can directly distinguish them by running electrical current along one direction, because of this anisotropic deformation, they will have different resistivities. Well, this concept has never materialized. It's not a concept that we now have in our mass-produced chips, and one of the main reasons for this is that unlike ferromagnetism, this type of spontaneous symmetry breaking, this nematic phase, seems to be much more subtle. It seems to rely on subtle correlated, it's a subtle correlated instability. And if we want to look into some systems where, and again, I will ask Eduardo what's the current status, whether it's fully established or people are still considering whether it's there or not. But in any case, it looks like it's a subtle phase that requires quite extreme external conditions. So one example where this has been explored extensively is our two-dimensional electron system, like in gallium arsenide, but in strong magnetic field, very low temperatures, and near the fractional quantum Hall state. And that's very different from ferromagnetic instability, which can occur in transition metals at room temperature, like cobalt, iron, and nickel.
There are examples where things are not that extreme.
Okay, good. I'll be very, very curious to hear about these examples.
Bilayer strontium ruthenate 327, there is a range of magnetic fields between 7 and 8 times level. You think that work. There is the nematic phase, which is actually observed in the transport. And then in addition to that, there are all these iron superconducting materials, like iron selenide. There's a huge phase, which is nematic.
Yes. So in the strontium, I don't know if the situation is already clear, because I was at a meeting where there was still a heated discussion whether it's really a true nematic phase or whether this is some structural things that are happening. So
we need to distinguish the symmetries of the phase from the microscopic mechanism. So there is a question whether it's orbital ordering or it has magnetic ordering, or it is what you call it, Pomeranchuk. Pomeranchuk, by the way, is a strong coupling interaction phase transition, and I don't know if there is a single example that justifies the use of Pomeranchuk. It's a nice tool for us theorists, but we need to distinguish the symmetries of the phase from the microscopic mechanisms behind the phase. And this is in that sense. Then people discuss, I mean, because they don't make this distinction, they say, no, it's orbital ordering or it's spin ordering, and that's irrelevant. Okay, what matters is what symmetry the state brings.
Good. So, thanks. So now we're going into our altermagnetic phase, and why we call this phase unconventional is because altermagnetism simultaneously breaks both the spin space rotation symmetry and the real space rotation symmetry. And if we want to see it in the momentum space first, what happens is that the original normal phase, which has the symmetry of the Fermi surface corresponding to the Hamiltonian, now in the altermagnetically ordered phase, we have this anisotropic deformation in each spin channel individually. And what you see is that the deformation axes are actually different. And because of this, we not only break the real space rotation symmetry, like in the nematic phase, but we also break the spin space rotation symmetry because we have spin polarized Fermi surfaces. But as emphasized here many times already during the during Libor's talk and the discussion, in altermagnets, what really plays an essential role is not only the electron-electron interaction term in the Hamiltonian, but also the single particle crystal potential term. It's actually the interplay between those two which is essential for the stability and robustness of the altermagnetic phase here. And there are also people in the audience who like the best model of the Leap lattice on which to demonstrate the altermagnetic phase. So let me do this. I also think that this arguably is the simplest crystal structure on which to demonstrate this. So this Leap lattice is a square lattice here. That means that the crystal potential has this fourfold real space rotation symmetry. So we have a fourfold real space rotation symmetry, and of course on top of this there is a full continuous spin space rotation symmetry, because neither of the two terms in the Hamiltonian have spin as an explicit parameter in it, so they both have the full spin rotation symmetry. But when you look at the ordered phase here, you see that first of all we now have the spin polarization. That means that the spin space rotation symmetry is broken. But also what you see here is now you cannot anymore rotate your crystal by 90 degrees because you would end up in a different state. So you also break the real space of fourfold rotation symmetry. But what is very important in ultramagnets is that there is a retained symmetry. There is still one symmetry which was already present in the non-magnetic phase that persists also in the ordered phase. And that's a symmetry which combines spin space rotation symmetry with the real space rotation it combines the spin space rotation with the real space rotation transformations. So what do we mean by this is that let's say I start with this state, and let me first apply the fourfold real space rotation on this state, and this is what happens. So I just rotate the lattice by 90 degrees, and what you see, I end up in a different state here. And yes, the fourfold real space rotation symmetry is broken. But when I now combine it with the twofold spin space rotation symmetry, that means I flip the spins or I change the colors. This is what happens is that I'm back to the original state. So individually, the two symmetries are broken, but a combination of these two operations is what is a symmetry of an altermagnetic system. And that's very important for altermagnets because this symmetry protects zero net magnetization, zero total magnetization in the system. Because my opposite spin densities in the crystal are connected with a symmetry. And that dictates that they fully compensate each other. Now, apart from the spin space and real space symmetries being broken, there is one very important symmetry which is also broken in an altermagnet. And here we don't have to get into the discussion whether it's in the momentum space or in the direct space, because it's actually in both. We have the broken time reversal symmetry. Now, that is reminiscent of ferromagnets, where also we have in both real space and the direct space and the momentum space, we break the time reversal symmetry. But it's of a very different form in ferromagnets, because in ferromagnets, in the momentum space, what we have this majority spin and minority spin Fermi surfaces, while the shape of the Fermi surfaces, or the orbital part, is actually still symmetric with respect to the crystal. We don't break the real space rotation symmetry, but we deform the Fermi surfaces in terms of their volume. So one Fermi surface becomes small and the other one becomes large. So we break the time reversal symmetry by simultaneously creating the net magnetization. While in altermagnets, we break the time reversal symmetry, but we have another symmetry that protects zero net magnetization. Now, because we have a time reversal symmetry breaking in altermagnets, both in the direct and in the momentum space, we also have the phenomenon that is essential for ferromagnetic spintronics, and that is the spin polarized electrical current. So this is the consequence of having the broken time reversal symmetry in the electronic structure. But again, if you look at these cartoons, you see that the nature of the spin polarized current in altermagnets is very distinct from ferromagnets. In ferromagnets, we have electrical current is spin polarized simply because we have more spin up electrons than if those electrons carry electrical current, this electrical current will be spin up polarized. In altermagnets is different. In altermagnets, we have spin polarized electrical current because we have different either magnitude of the spin or different magnitude of the electrical currents in the two channels, or we have different deflection angles of the electrical currents in the two channels with respect to the applied bias voltage. Okay, so it now depends which way you apply bias with respect to your crystal, and you can either have different magnitudes of the electrical currents in the two channels, or you can have different deflection angles. And this is a consequence of this anisotropic deformation of each individual a Fermi surface. This makes the transport anisotropic, but also the mutual rotation of these deformation axes, which can result in these different magnitudes or different deflection angles for the two spin channels. And of course, because we break time reversal symmetry in the electronic structure, we also have the property when we go to the time reverse state of our system, that means when we flip the spins, when we flip the order, also the polarization of the electrical current changes sign. So this is the same as in ferromagnets. So these ideas, which were brought forward theoretically, and also the strength of these effects have been estimated in some altermagnets and been estimated to be of the comparable strength as in conventional ferromagnets. That motivated our colleagues, experimentalists, to put these ideas under the test. And so this is the first experiment I'd like to talk about, is an experiment done in manganese-5 silicon-3, which is a compensated magnet. But when you have it in thin films, there's been indirect evidence, both from experiment and also from theory, that it might be a an ultramagnet with this characteristic D-wave altermagnetic type of order, or D-wave Fermi surfaces. So our colleagues experimentally said, okay, so we're going to try to see if this compensated magnet can generate spin polarized electrical current. Now, what we've seen before, when I showed you the device, which is already in the integrated circuits, this is the spin valve or magnetic tunnel junction. Here you have the two magnetic electrodes which are separated just by a nanometer, sometimes even a fraction of a nanometer. So the injecting electrode, the detecting electrode, and also the transport channel are virtually in the same place. So these are sort of local devices. But when people are trying to study spin transport experimentally, they like to disentangle spin injection from spin transport and from the detection of the spin. And for this, they use this lateral spin valve device, in which what you see is an injection electrode. Then there is a channel through which the spins can transport the spin information, and then there is this detection electrode here. And as you see from the scale here, the injection and detection electrode can be separated hundreds of nanometers. So we talk about non-local spin device or non-local spin detection.
Could you quickly clarify why this is a D-wave? The picture there? I couldn't see the rotation that I can do to get the spin up to the spin down.
Yes, it's actually a twofold rotation. So you don't have to have necessarily a fourfold rotation to connecting the opposite sublattices in a D-wave. You can have a twofold. When you do not have a 90-degree angle, but you have, for example, 60-degree angle, you do this, right?
Yeah.
So it's a
Okay.
so it's a rotation axis along this nodal.
Okay, got it. Thank you.
Okay. Yeah. So this is the device. So the interesting one, the one we're particularly interested in, this one with the compensated magnetic manganese-5 silicon-3 injection electrode. But as you see, our colleagues fabricated a control device, a reference device, in which not only the detection electrode, which is ordinary permalloy, nickel iron, but also the injection electrode is ferromagnetic, so that we can confirm that everything is fine in terms of electrical and spin detection behavior of such a device. So because we have the reference, let me just first go through the experiment on the reference device. So this has been done many times, non-local spin detection in this lateral spin valve. So the first typical geometry in which you inject the spins into this channel is that you apply electrical bias between the ferromagnetic injection electrode and the spin channel here. So imagine that this is a non-magnetic copper channel, and here is my ferromagnetic injection electrode. So you basically push the spin down electrons from the ferromagnet into the channel. Now the electrical current is then drained here on one side of the device, while towards the other end of the channel, the spins which were injected into the channel now diffuse as a pure spin current, no electrical current associated. They diffuse towards the second magnetic electrode where they are detected in the form of this non-local voltage here. So this is the setup of the experiment. Now what experimentalists can do, they can apply magnetic field. So they can apply magnetic field along the magnetization of these electrodes. And at some point what you see is that the detection electrode flips. So this is how the experimentalists check that the non-local signal that they measure is of spin origin. Because if this non-local signal changes sign upon flipping the magnetization of the detection electrode, that's a signature that the non-local voltage originates from spin signal. And then finally, further increasing the magnetic field, you also can switch the injection electrode. And then when you again see the switching of the non-local voltage here, that tells you that the spin injection is time reversal symmetry breaking. That actually you flip the sign of the spins when you flip the sign of the magnetization of the injection electrode. And so this is the real experimental data, and it's exactly the same phenomenology. So you start increasing the magnetic field or sweeping the magnetic field. And here you see the first transition. This is where the detection electrode flips. And then you continue, and you see the second transition, and this is where the injection electrode flips. Now, you can also try in this device to apply the bias not between the injection electrode and the channel, but just along the injection electrode itself. here your electrons, the spin polarized electrons, will just propagate along your injection electrode, but not into the channel. And as a result, experimentally, you would not observe any signal on this device. So now let's take a look what happens if instead of the ferromagnetic permalloy, I use the manganese-5 silicon-3. So again, this is now my injection electrode. Now the picture is just mirror image because this is how they made their device. You know, the reference and the manganese-5 silicon-3 spin valves are actually mirror images. So now here I am biasing my injection electrode and the channel. So this is how I apply my bias, hoping to inject spin polarized electrons into the channel, and then they will diffuse towards the detection electrode where I will detect it. And here is the experimental result. And again, you see the first switching, which is due to the switching of the detection ferromagnetic electrode. I know exactly at what magnetic field this is supposed to happen. And then at a higher magnetic field, I see the other switching. It switches back. So it just suggests that indeed we have the time reversal symmetry breaking spin injection in our non-local spin valve, which however is made of this compensated manganese-5 silicon-3. Now here is the magnetization measurement of the manganese-5 silicon-3, and as you see there is negligible, unmeasurable net magnetization, net remnant magnetization. So this is very different from our ferromagnetic electrode where you will see a sizable magnetization. In the manganese-5 silicon-3, we cannot detect it in these thin films, any sizable net magnetization. So then you can ask a question, so how do I know that by the magnetic field I actually reversed the state? I generated the time reverse state in the compensated magnet. And this we know from measuring the anomalous Hall effect. Because as has been already emphasized here today, anomalous Hall effect is a phenomenon that requires time reversal symmetry breaking. So if I measure the anomalous Hall effect and if I see flipping of the sign, that's a signature, experimental signature, that I also time reverse the magnetic order. Now, the remarkable thing that our colleagues did in these experiments is that they actually fabricated the Hall cross at the very same electrode, which they also use as the injection electrode in the non-local spin valve. So they can directly compare the magnetic fields at which they switch the magnetic order by measuring the anomalous Hall effect with the magnetic field at which they see the switching in the non-local spin valve. They are not exactly the same, but they are nearly the same. And they are not exactly the same because you're also not exactly at the same point where you do the measurement. But it is a convincing evidence that indeed what we see, the second switching, is due to the reversal of the magnetic order in this compensated magnet. Go ahead.
The moment is in the plane?
The moments are God knows where. We definitely know that they are not out of plane, right? Because if they were out of plane, we will not be able to measure anomalous Hall effect. So they have to have an in-plane component.
But I think even that it needs to be along. This is a hexagonal lattice or triangular lattice.
This is a D-wave magnet. So it is.
So if you
it is, you know, I will show you later how it's kind of complex. It's a hexagonal lattice, but it's a rectangular order. I will show you the image.
So complicated.
Yeah. It's going to be the next slide when I will show it to you. Okay. So.
What can I quickly ask? Do you have a microscopic understanding why applying a magnetic field would actually switch the orientation of the nail order?
So.
Like you assume that there's spin flop or spin counting.
Yeah, so this is a general comment to virtually all altermagnets, is that they have, and in particular when you see anomalous Hall effect, that also means that they have, by symmetry, allowed the weak magnetization. An external magnetic field can couple to the weak magnetization, the relativistic one, and the weak magnetization tends to be coupled to the nail order by, for example, DMI or some relativistic terms that couple nail vector and the weak magnetization. So the idea is that external magnetic field couples to the magnetization, switches it, and then magnetization is coupled to the nail vector, so it switches also the nail vector. And this is how it's controlled in all these experimental manganese telluride or in all the other altermagnets when you can control the sign of the order by magnetic field. Yes?
explain again why there's no current flowing? You said there's no current going through, but how is spin transported?
Yeah, so so in these devices, this is how they do the experiment. So the bias, that means the electrical voltage, is applied between this contact and here this contact, okay? So this is where the electrical current is flowing, but there is no current flowing in this direction because there is no bias here. But what happens is that as you push the spin polarized electrons into this channel, there is a non-equilibrium occupation of spin up and spin down states, and because you basically flip in the non-equilibrium state, you flip the chemical potential of the spin up and spin down electrons, then there is a gradient of that, and so they will diffuse. So there's a diffusive spin transport in the opposite direction. And so the spins are diffusing, and then they create a non-equilibrium chemical potentials on the other hand, and you can measure it as a voltage on the other side. Okay?
Like an equilibrium property, basically.
Sorry?
So it's kind of like an equilibrium property of the Fermi surface of the...
It's non-equilibrium effect. It's basically you drive the chemical potentials out of equilibrium, and out of equilibrium the chemical potentials of the spin up and spin down electrons do not have to be the same. Okay? Okay. Yes?
Another question about if you compare the ferromagnetic and the manganese-silicon result, it seems like there's a sort of sloped background on the manganese-silicon results on the resistivity. Do you have an explanation of it? There and not with the ferromagnetic.
Yeah, so what you also see here is that there is a nice single switching here, while here you have multiple steps in the switching. So this is understood in terms of domains, so that you're gradually switching, you have multiple domains, and you also see it in the anomalous Hall effect. Here you also see some multiple steps, so not complete switching maybe. Okay. So very good. So this was the experiment, which was completely analogous to the experiment with the ferromagnetic electrode. But now let's try the other one. Now let's try to bias the manganese 5 silicon 3 in this geometry, where you actually apply the bias just along the injection electrode. So in ferromagnets, this does not lead to a spin signal. But when you look experimentally into our manganese 5 silicon 3, you see that there is a signal, and the signal is actually analogous to the signal which you get in this sort of ordinary biasing geometry. So that's very unconventional. People have not observed this with ferromagnetic injectors. But with the picture of the altermagnetic order, you can understand it very straightforwardly, because as we explained, so now here's the answer to who was asking about, you were asking about hexagonal. So this is the lattice. It's hexagonal. In non-magnetic phase, you have these 6 equivalent manganese atoms, but in the ordered phase, and that's known from neutrons, only 4 of them are magnetically ordered. So they form this D-wave type of altermagnetic order. And this is the orientation of the D-wave order with respect to the crystal lattice, which are aligned with the device. So it's all aligned in the proper way. And so what you see here in this biasing geometry, which is, let's say, the ordinary biasing geometry, you see that there is different magnitude and slightly different deflection angle between the up and down spins, right? But in total, what you see that in the horizontal direction, you will have majority spins pointing down, the red spins. So you inject spin polarized current. Now, in this biasing geometry, again, you have different magnitudes, but also different deflection angles. So you have not only the longitudinal part of the electrical currents in the 2 channels, but you also have a transverse component, in particular for the spin down electrons. So that, just finishing the sentence, that explains that even if you're biasing along the electrode, you will have a component of a spin polarized current which is going into the channel. Go ahead.
So where is because there's a dy, where's the by with respect to the axis that are showing you? Because I expected that you would have...
It's all oriented. It should be all arrows should be the real. So by is really along, no, sorry, by is, the arrow means that I'm increasing the magnetic field, but y axis is the vertical axis along the magnetization.
Which is out of plane?
No, which is in plane along, which is along the the electrode, because the electrode has a shape anisotropy, and that defines the magnetization which is along the electrode.
Oh, well, that's because you have a shape in it.
Yeah, so it's an in-plane permalloy, so it will be weakly anisotropic, but because of the shape anisotropy, you make it along
but
that.
the anomalous Hall then would be RXZ in this.
Now the anomalous Hall. That's interesting. This is altermagnet.
Yeah.
This is not the permalloy. This is the anomalous Hall effect in the altermagnet. You can apply the magnetic field either out of plane or in plane, and you can still switch the Néel order, and you see the anomalous Hall effect. Okay, so this is really Y magnetic field, so along the y-axis.
Okay.
It's very different from a ferromagnet, what you're usually used to. Yes?
Just a question clarifying the geometry. So the D-wave plane, is it misaligned with the plane of the lattice device so that the spin splitter current can actually be...
No, this is really the plane. These two axes is really in plane. This is all in the plane of the device.
I may be missing the argument. How can then the spin splitter actually produce the current in the direction of the permalloy? How would the spin enter the spin?
So in this biasing geometry, you have a bias along injecting into the copper channel, right? So you see you have a component of the bias which is along this direction. So for this bias, you see I have different number of spin up and spin down electrons, right? When you see at this, that you understand. Here, when I apply the bias in the vertical direction or along the y-axis, I have no contribution from the spin up electrons, because they are all going in the vertical direction. They have no component into the copper, right? But I have for the red electrons, for the spin down electrons, I have both vertical but also horizontal component. Because the down electrons, because of the tilted Fermi surface here, right? Their current is deflected from the applied bias. Okay? Here, for the blue ones, the ellipse is not has the axis of the ellipse is along the applied bias, so there's no deflection, right?
So the cross of the orange and the white line is actually made of the same material, so right?
Cross of the orange. No. The orange is the manganese 5 silicon 3, the white is the copper, and the green is the permalloy.
I'll ask you later. That's fine. Please continue.
More questions?
I have a very different question. So, because I'm intrigued by this ordering of 4 out of the 6 spins. Right? These are manganese D5, probably large moments sitting there. So is the idea that the moments that are, let's say, that you indicate without an arrow there, kind of pointing in an arbitrary direction?
Yeah, they don't have a net magnetization. And this is seen in neutrons. But you might wonder why these 4 and not, for example, these 4, right? This is actually energetically equivalent, identical, and we indeed could have these variants. Okay, in the sample, you can have either these 4, or there are 2 other possibilities where you have 4 occupied. Now, if you would go through this argument, then there is 1 out of the 2 which will give you exactly the same polarization of the current, and the third one will give you none, will give you 0. So that does not contribute. So we may have more of these variants in the sample because we don't have good control, but we know that the net effect would be a net spin polarization.
Yeah, so
Okay.
it would be different domains. But
Yeah.
at some lower temperature, you would expect that this entropy that these 2 non-order spins have, that this entropy somehow will, there should be another ordering.
There is. Yeah, there is. There is a first transition from paramagnetic to this collinear phase. And then there is a second transition, which is depends whether it's a thin film or bulk. And we can have a long discussion what happens with the difference between thin films and bulk, because it's crucial. In bulk, there is no altermagnetic order. Because you have this, but plus doubling of the unit cell in the bulk. And they don't see an anomalous Hall effect, etc., etc. But in thin films, and also there is a structural transition in bulk, which we don't see in the films, because films are clamped to the substrate, etc. So there's a fairly long story. But anyway, there is a lower temperature phase transition into a non-collinear, non-coplanar phase, which Libors likes very much, because it's a p-wave magnet. Okay?
But do they have moments in the other two manganese in the lower phase?
In the lower phase, they become moments also in those ones. Yeah, go ahead.
So in this explanation where you draw the arrow representing the bias,
Yes.
so normally in the spin splitter context, you would have the current flowing in your altermagnet, and you would generate spin polarized currents. But here the bias is applied across the interface with copper.
You mean the top one or the bottom one? Which geometry are we talking about? This one or this one?
Let's say the bottom one.
The bottom one, okay.
So you apply the bias between the altermagnet and copper, and what you see then is the splitting of the chemical potential. So the sign of that would be a representation of the spin asymmetry and the spin injection, which is actually an out-of-plane process that's where current is injected in the z direction. So how is that related to the sign of bias in the plane? Isn't that a different?
Yeah, it's a very good question. So is Cairo here? I mean, this is again going a little out of hand, but is that okay? I mean, shoot me. I mean, I don't know. It's because these are great questions. So in the normal non-local spin valve, where you have the ferromagnetic injector, and we can also talk about injector from non-magnetic platinum, where there's also interesting phenomenology. What happens is that you have the injection electrode, and then you have the copper channel. And most of the injection is actually happening when you bias it in the vertical direction through the horizontal interface. The spins are injected into the top copper channel, right? So it's that interface that then matters. Now, but you can also imagine, because how the device looks like is that there's a lithography, and then the copper channel goes like this, and then it continues. So you can also have injection from the sidewall here, okay? Now, these people who did this experiment were actually extremely careful, and they showed that if you don't properly treat the sidewall by lithography, and that means you have to do very gentle lithography and treat the surface. If they don't do this, then they don't see in the manganese-5 silicon-3 the signal. Only if they have a properly treated sidewall interface, they see the spin injection, which confirms that in this device the injection is actually from the sidewall. While in the reference device with the ferromagnetic injection electrode, it didn't matter, because the injection is really through the vertical interface here, okay? So that's also different from the spin hall, because people can also use platinum and do the spin hall. The spin hall current is also the vertical one, which is normally dominating the spin injection. But here, it's actually the lateral one.
Right, but could you exclude the fact that your interfacial structure itself prefers a particular spin sublattice at the interface, in which case you would have preferential spin injection for one spin, but not due to the band structure, but just to the interfacial structure?
I cannot exclude many things in this experiment, okay? So the only thing that is an absolutely, for me, undisputable experimental fact is that this is a compensated magnet in which I can do spin injection in this non-local spin valve geometry, okay? I also, experimental fact is that I can see it in both biasing geometries. That's already quite unconventional compared to normal ferromagnets. And also experimental fact is that if I don't have a proper sidewall interface, I don't see it. So these are experimental facts. The rest, the altermagnetic interpretation, I'm just presenting as something that could explain the effect. It actually can explain it even semi-quantitatively if you account for the sidewall injection. So that's actually pretty impressive. But I'm not saying that it's an ambiguous, I have an ambiguous experimental proof that it must be this. And we don't actually have from neutrons in these thin films an unambiguous proof that we have this altermagnetic phase to start with in manganese-5 silicon-3. And it's notoriously difficult actually in thin films to get reliable neutron to say that. So all the rest was this interpretation was indirect, but the experimental facts that I mentioned are direct. Okay. Does that?
Yeah. I mean, of course, without altermagnetism, you wouldn't have anything. But in an altermagnetic phase, you could have a situation where the interface lowers the symmetry in such a way that your two sublattices present unequally at the surface. So your surface would be polarized because of that, and not because of the reciprocal space.
Yeah, it could be, but the altermagnetic phase, without any of these additional effects, can explain it not only qualitatively but also semi-quantitatively. So that's the only answer I can give you. But I can definitely not exclude.
The plate strain
Yeah.
and sphere polarization.
Jairo. I have maybe 5 minutes with the other experiment, but I don't, again, you guys tell me, okay? Okay. So, switching gears. Now we're switching gears to manganese telluride, which actually is, for which we do have convincing evidence from neutrons, from ARPES measurements that this is an altermagnet. It belongs together with the chromium antimony into this hexagonal family of systems which are not D-wave. So far what I discussed was a D-wave altermagnet. So this, sorry?
It's called the dice lattice.
Dice lattice, okay. So this is a G-wave altermagnet because we have this hexagonal lattice which actually generates a symmetry which is spin rotation together with a 6-fold real space rotation transformation. And as a result, we do not have 2, but we have 4 spin-degenerate nodal surfaces in the momentum space Brillouin zone of the non-relativistic electronic structure. And as a result, you have spin polarization outside these 4 spin-degenerate nodal planes, the strong non-relativistic spin polarization. So that has been studied. It has been studied in these earlier papers, also by spin and angular resolved photo emission experiments. But there is one important limitation if you go beyond D-wave. If you go to the higher symmetry ones, G-wave or I-wave, is that the bulk electrical current is not spin polarized. And now actually independent of where you apply the bias, if you're beyond the D-wave, if you go to G-wave or I-wave, the electrical current is not polarized. That doesn't mean, finishing the sentence, that you cannot have spin-dependent transport effects. If it's an interfacial effect, like for example tunneling magnetoresistance, you can have strong tunnel magnetoresistance in GMR. But the bulk conductivity is spin-independent, yes?
But this is if you don't have spin orbital current, right?
Yes, this is the non-relativistic one. And there we go. So if you want to have a spin-dependent, yes, if you want to have a spin-dependent, spoiler it. You got it, guys.
So that you have a rectangular.
Can't you cut it?
Like, I mean, can't you cut it diagonally? So you have, like, again, I mean, your system before also wasn't like square or like rectangular symmetry, right? I mean, for like the chromium antimony, if I make like a 110 or something surface.
Maybe we're going there. So what I'm saying is that if you have a bulk crystal and you're talking about the bulk conductivity, it is not going to be spin dependent, okay? So if you want to get something spin dependent out of this, you have to somehow lower the symmetry. It could be that you're using interfaces, but it could be that you lower the symmetry by some other means. And the other means that I want to show now is relativistic spin-orbit coupling, okay? So relativistic spin-orbit coupling lowers the symmetry because you see that now is spin even in the Hamiltonian, so you break the spin rotation symmetries already on the level of the Hamiltonian. It lowers the symmetry. And so what happens is, one of the particular demonstrations, and I believe Libor already mentioned this, is that if I look at this kz equals 0 nodal spin degenerate plane in the non-relativistic electronic structure, when I turn on spin-orbit coupling, I see that there is a spin polarized Fermi surface at the kz equals 0 plane, and it has this D-wave-like symmetry. It has these 2 Fermi surfaces that are anisotropic. And so it has low enough symmetry that you will have spin-dependent conductivity in the bulk. You don't have to chop the crystal. It's just because of adding spin-orbit coupling. Now your spin, your electrical currents can depend on spin. Again, now it will depend which way you apply bias, but it will start to behave like a D-wave altermagnet because of the spin-orbit coupling. So again, this was so challenging or intriguing to experimentalists that they want to see it. And now, not in transport or a spintronic effect, but directly by spin-resolved photoemission ARPES. And so if you want to see in spin-resolved photoemission experiment such a spin polarization, the first thing and the most important thing you have to have is a single domain sample. Single domain in terms of crystal domains, but also in terms of the time reverse domains. You have to have one such that you can detect the net spin polarization. So here is how our experimentalists do this. And if the previous experiment was very simple, right? I needed just one slide, but it took them 1.5 years to complete this experiment. This is a 2 years effort, again, on 2 slides. First, you need to start with a perfect single crystal epilayer. So this is manganese telluride grown by molecular beam epitaxy, virtually without any defects on a large scale. Now, if you want to now, you have this hexagonal lattice, and this hexagonal lattice has basically 3 equivalent easy axes in the plane. But they can choose which of the easy axes they will get by making bars which are of, let's say, few microns width. And if you make these bars, the easy axis, because of magnetic anisotropy, will choose to align along the bar direction. So they can now choose one out of these 3, but they cannot distinguish the time reversed domains. So they cannot distinguish just the crystal domains. So how to distinguish between the time reverse domains is by performing a field cooling experiment. So they are field cooling the sample in one or the opposite direction. So this is the virgin sample where you see that you have a 50-50 of, let's say, one domain and the time reverse domain corresponding these 2 Fermi surfaces with opposite spin polarization. So you would not be able to measure spin resolved ARPES. But if they do field cooling, they can prefer one. And then they can choose. It could be either brown or blue, depending on the sign of the magnetic field they apply during field cooling. And now the thing that I would like to emphasize is that at the end of the story, they get these very clean ARPES Fermi surfaces and also band structures. But the, to me, absolutely remarkable thing is that from here to here, they did it without breaking vacuum. And this is what you really have to do if you want to do high resolution spin resolved ARPES, have as perfect surfaces as possible. So from the growth, including the patterning, including the field cooling, all the way to the ARPES, the high vacuum has never been broken. Which also means that you have to actually grow to start with in MBE on already pre-patterned substrates.
This is regular ARPES, though.
This is regular ARPES, and this is spin resolved ARPES. Okay, so final slide. Okay.
Can I ask you, I'm a bit confused, but if I look at those, any of those pictures, that they have 2-fold symmetry and not 3-fold. So you just switch off spin-over coupling. That doesn't lower the symmetry.
It does, because you have the nail vector. Sorry, I'm going in the wrong direction.
Oh, the nail vector is in the plane.
The nail vector is in the plane, and the nail vector lowers the symmetry. And therefore, depending on which of the 3 easy axes you have these 3 different, you can have 3 different rotations of the Fermi surface, okay? So, so this is spin unresolved ARPES, and this is spin resolved ARPES. So you basically make cuts through your Fermi surface. This is the cut about 200 millivolts. And this is measuring in one domain. Then they time reverse the domain by opposite field cooling. And then by looking in the same chip, they have patterned the bars along these 3 different directions. So it's the same measurement, the same geometry of the ARPES, which was absolutely critical, because geometry of ARPES, if you change, things change. So this is a completely consistent set of measurements where everything is controlled by the sample, not by the ARPES setup, and they see these consistent signs of the polarization. This is a purely KZ equals 0 measurement. They know from scanning energies. So they can determine at which KZ they are by making scans. They scan the energy and they compare it. Yeah.
But they compare with some.
Yeah, they compare it, and they can tune. They can tune it and find that their KZ equals 0. That's it. Thanks a lot.